One is that we may as well, once we know how to count, we can do the number line. So number line is actually any line, but for convenience, we standardize it to be something horizontal. And for the rest of the institute, we won't be doing any negative numbers. The number line goes two directions, but so we only look at the right side of the number line. This is another tradition. We always pick a point and say that's 0. What we do is that we know how to count now, right? 0, 2, 3, 4, and up to 5 billion, 5 billion, 2 billion, right? We want to put, instead of just counting and just talking about it, we put them on the line so that you can actually see it. So what we do is the following. We decide ahead of time already that we want to only look at the right side of the number line, which means for our purpose, anything, we only concentrate on things to the right of the number 0. You pick a random number 0 and that's good. Now, the next move is the most critical, which is you decide, you tell me, or you make a decision where you want to put the 1 in. Once the 1 is in there, then the rest is completely determined in the following sense. You have a segment, line segment. You replicate this all the way down. And then what happened is that another segment down here, that point, that marker, we call it 2. Another point down, equal distance, so you have equal distance skipping, so to speak. And that's 3, and so on. And now you just keep going. To us, that's the number line. Now, the acceptance of the number line by now is pretty firmly based. But some 10 years ago, for example, there was a teacher was in horror. So he said, you look at number line, they was basically wanting to bolt upon this because the whole institute is based on looking at number line. Now let me convince you philosophically that this is something you ought to look at. So you've gone through at least K-12 mathematics. Look back on it. Have you ever gotten away from the x-axis in your whole life? Can you ever do any mathematics by staying away from the x-y axis your whole life? Any mathematics you do after 5th grade, it's all about, always start with a x-y axis. But that's the number line. That is the number line. The x-axis, or the y-axis for that matter, except the y-axis simply goes vertically, so we don't want to look at it, that's all. So the number line is truly basic. And in higher mathematics, of course, everything is just the number line. The axis, all dimensions, we have to have a set of axes to do any work. So it's best to introduce children to number line as early as you can. In fact, the earlier the better. If you are doing K-2, for example, by all means, slow. By 2, they should be fluent in it, but starting with K, show them the line. In grade 1, you already start to put, they can count, put the markers on, and make them get used to it. In the Common Core curriculum, standards, number line is officially in place in grade 2, I think. Maybe earlier, but in any case, grade 2 definitely is in play. And then, of course, the Common Core curriculum standards makes extensive use of the number line as it should. So these are good things to remember. So the advantage of the number line is that, as I said, up to this point we just keep counting, write the numbers down. That's the basic part, yes. On the other hand, I think it's actually psychological. Cognitive psychologists have done a study on the human brain, and they established the fact that somehow we are all born with a number line. It's sort of hardwired in our brains that we have a good perception of equal distance, and in our mind we can see this moving down equal distance down. we should not overdo it, but I claiming too much, much more than that. No, I don't think we can't, as far as I know. Cognitive science hasn't established that. But the general concept, outline of having a number line in our brains, that's absolutely beyond controversy. Right? So, so knowing that, it should make you feel better when you go teach your children number line. You know you have a lot of scientific backing, a lot of educational backing behind it. Okay, now, so we mentioned it now, but we cannot help keep repeating, mentioning this fact. So that's one thing. But the other thing is skip counting. What is skip counting, actually? We can skip count by any, as you all know, right? By 3, by 5, by 8. But most important to us is to skip count by 10, or skip count by 100, or skip count by 1,000, skip count by 10 times 10 times 10, no matter how many copies. Why we do that? Well, first of all, let me ask you a question. What's this equal to? Everybody knows, right? You know what my next question is? Why? All right? You want to try to explain it? Why? Why?
1 times 58 is 56.
1 times 58 is 58, yes. What about 100, 1,000? What about 1,000? This is 1,000.
58,000.
Have you ever done it? Okay, now that's coming attraction. So I just want to tell you why we're paying attention to skip counting. That's maybe we want to explain. This is learning is a rote skill, right? You see, you just attach the zeros to it. Move the zeros over. That's what you teach every kid. But you should do better than that, obviously. Don't you agree? Yeah. Sorry. What?
Are you still asking why it is that?
Yeah, sure.
So if we're talking about number line, what you can say is, if you hop 1,000 times, you'll end up at 58,000 on the number line. And if you hop 1,058 times, you'll end up at 58,000 on the number line.
How do you know?
I've done it. I've done enough of those things to know that will be the same, because I've done it with smaller numbers. And I know that there's a pattern involved.
But smaller number is not the same as big number.
Yeah,
Right.
no, I know.
Right?
But
So
I've done
it's
it.
like this. It's like this. We're doing 2 fractions, right? So 1/3 and less than 1/2. Everybody knows that because 1/3, 1/2. Everybody sees that. So what you see is 1 to the left, right. Alright, so I'll explain that. You agree? You agree this is correct?
Yes, yes.
All right. I'll explain that. So I mean, you just because you've seen something that, well, for a small number doesn't mean that you know the reason. You just say, well, seeing is believing. Yeah, seeing is believing. This much. Yes.
But that's, I mean, I'll explain that too.
Okay, good.
Well, because if you've got a fraction if you've got one whole and they're equal wholes, and you divide this one into one part more than the other one, then this one's going to be smaller
How do
parts.
you know that? I've never done it.
I'm going to go with the same thing that I said before. I've done it often enough to know that every single time if I divide it by a larger, in just many more pieces gives you a smaller fraction.
That's what we call the beginning of a discussion. But we usually end it with that, right? And what I'm trying to get you to do is to do better. You cannot leave your children hanging, dangling in midair, basically. That's what it is. You know, well, you vaguely see this, so now you believe it. Now, how far can you go with that philosophy? Well, you vaguely see this, so therefore you must believe it. Well, okay, does the sun revolve around the earth? You see it, don't you? Is that how you teach your kids? Well, you see it, well, so it must be true. That's true.
No,
No, you don't want to do that, right?
No, don't want to do that.
So you should know there's a limitation that for first graders, obviously, that's good enough. I mean, for first graders, well, if they get to that, but this is second graders, that's plenty good. Give them a line, kind of go 3 halves, get 2, and say measure which is big. That's good. But they can't go through their whole lives just saying, that's all I know and that's all I need to know my whole life, right? That's not. They should be able to convince themselves of this. So what we're trying to do here is to try to explain everything completely impossible. And we usually do explain completely, right? So I tried by way of introducing skip counting, and you wonder why? Well, the reason is ultimately I want to explain such things. So skip counting, as I said, I'm more interested in skip counting by 10. Then you can do skip count by 100 and so on, because it's just a matter of writing more, right? So in that case, it's really true that you can do it by 10, you know that the same thing will apply. Now, from our point of view, skip counting by 10 has a very direct visual representation. For example, yeah. So all the way to 9, of course. And that's 19. So rows of 10s. So 2, 1, 2, 3, 4, and then 9, 3, 0, 3, 1, 3, 2, 3, 3, and 3, 9, and so on. Okay? Now, so let me say I skip count starting here by 10. Then to us, skip count by 10 is not some vague concept. You know exactly what it is, right? Well, you skip count by 10 means what? That's all. If I skip count by 10, I write out a chart of 2-digit numbers. I want to skip count by 100, then I do 3-digit numbers. But it's just directly what it is coming down the table, the list. But in particular, I skip count by. What's that?
Card. It's a card.
Oh, not for me.
It's a new bird.
Electric. Outburst. Okay. Skip count by 10. Starting with 0. The next step is 10. Next step is 20, 30. Now, the interesting question is, I skip count by 10. The fifth step gets to where? 50. 50, right? First step is 10. Second step, 2. So, first step is 50, right? 9th step is what? Skip counting by 10, starting with 0. 9th step is what? 90. And the 10th step? 100. So, now, once you are pointing out, then you can know exactly. So let me write this first, right? So, skip count. 10 from 0. Then what you have is If I, for the same reason, if you skip count by 100, starting from 0, then it's exactly the same principle, no? It's 100, 200, 300, 900, and then 1,000. I hope it's quite clear. Right? Now, this may not impress you very much, but in fact, this has everything to do with what we're trying to do. To understand multiplication by 100, 1,000, whatever. Right? Now, to express this correctly, we introduce the two basic arithmetic operations. One is addition. What's addition? 1 is 7 plus 2. What does that mean? So what does that mean?
How many steps from 7?
Right.
2 steps.
2 steps counting from 7. Right? So 6, 7, 8, 9, 10, 11. So from 7, right? 1 step, 2 steps. So it's 9. Now, we're introducing the equal sign for the first time here. I write this. It means what? That the two sides express the same number. Now, the equal sign is used very carefully for us. Right now, I just say the equality sign simply means the two sides of this equal sign are numbers that are the same number. What do I mean by same number? That means you keep counting, you come across that number. No matter how you do it, it's this side or that side. So in general, n plus n, yeah, is the number obtained by counting n steps starting from n. So now, at this point, I think you appreciate the fact that we were so careful with the concept of counting. We say explicitly from what to what. Because if you say 92, you say, normally you say 2 numbers beyond 7 or something like that. Well, how do you count 2 numbers beyond 7? Well, what do you mean by 2 numbers beyond 7? I could equally say first number, second number. 2 numbers beyond 7. Which is the first number? So that's why we say explicitly counting from 7, 2 steps. There is no ambiguity. So you have to be very careful when you do this in the class. And this is why the precision of language, and that's why I'm trying to impress on you. When you do your homework, try to be as precise as you can. And I'm sure Winnie and Stephanie and Sunil would catch you, or at least some of the time. That slippery language would get you into a lot of trouble. So this is a lesson I learned from doing this. At the beginning, I would say, well, we were I wasn't aware of the problem. Okay. Well, 2 numbers beyond 7, and then 2 numbers 1, 2. Or well, that's not but 5 numbers beyond 7. Then you say 1, 2, 3, 4, 6, 7. You count like that, and it's hard to tell. Are you doing the right thing or not? Well, who says, right? Okay, so this is our concept of addition. With that understood, you see? So what is it? Now, this fact has a much more dignified expression. This is the expression. Now, to summarize these 2 facts is what? 10 plus 10, right? Now, first of all, when we say, in general, when we say this, now you see, This we know what it means already, right? It's 10 steps counting from the 10. Right? Now, when I do that, then we have to have an understanding. When I do this without any parentheses or any add-ons, it means do this first, and then do this, and then do that. Right? So I'm going to keep 10 plus 10 times. That means what? You count 10 steps from 10. You get somewhere. And then count 10 steps from this number, whatever it is, get someplace. And then count 10 steps from whatever this number is, get there. So on. So it's understood to be just continuous from left to right. With no further parentheses, no nothing. Yeah?
But 10 steps from 10 would be 110 when you want to start with a 0, so you end up with 100.
Oh yeah, but you give me the answer, right? Is that what you're trying to tell me?
Oh, I'm just like, I'm wondering why you didn't start with 0, because 10 steps from 10 would be 110, not 100.
No. I mean, yeah, no, sorry. You get the 10 by starting with 0 and 10 steps. Sorry, right? That's the first 10. So I'm trying to express it exactly, right? So there, what you don't like, you don't do that. You see, you don't do that. Mm-hmm. You always start with the non-zero number, correct? Normally. But then you get to that by counting from 0 in 10 steps. So that's the implicit. So what this says is that, right? Now you only have 9 additions here, you see. Yeah, so I should point that out, right? You want to add 10 tens. There are only 9 addition symbols, right? So you say, you start with 0, count, skip count 10 times by 10, right? So the implicit rule is have that 2, 3, 4, 5, 6, 7, 9, 10. So this expresses the end result of the skip counting. See what I'm saying? So this is our way of saying, in this language, it's totally unambiguous. But in this language, you have to realize you're doing exactly the same thing. If you go back to 0 and skip count by 10 times, then adding 10 to itself 10 times means skip count, 9 times. If you start from 0. But you think of that as skip counting from, skip count from 10, sorry. So you start with number 10, skip count by 10, 9 times, you get 100. Right? That's it. But conceptually, you think of this 10 as being already a skip of 10 skip 10 steps from 0 to get here first. Then all together, just skip count by 10 times.
Then you get 100.
Did that confuse anyone?
Yeah, because you start by saying 10.
Sorry?
When you start counting by the skip counting, you start by saying 10. You don't go on. That's why it kind of explains your first. This is your first skip. You're landed on 10.
Yes, you already landed. Yes,
Landed on
yes,
10,
yes.
and then you keep going. Yeah.
Yes. So to express this, you're saying 100. That's 100 plus 100 10 times. Give you a lot. You should understand. I'm not trying to tell you you're learning this for the first time. You know that. I'm trying to tell you how you know that. On a basis that's straightforward enough that you can explain it, actually say it. I mean, normally you just look at this and say, well, you know, you fudge the number of zeros, something like that. So I'm trying to make you understand why we think counting is so important. That's one example. This is the result of careful counting. Okay. Now the second concept we want to introduce, and you know that too, is that certain kinds of additions are so special that we can abbreviate and give them a different name. Right? 7 plus 7 plus 7 plus 7. Such additions come up more often than you realize. Or in fact, maybe you already realize it. This happens all the time. You're the same number, but adding to itself many times. So in this case, you're adding to itself 4 times, right? So our definition is, this is a symbol of saying, once we see this, we introduce a shorthand notation, which is 4 times 6. In other words, this is the addition only. As far as whole number is concerned. Multiplication is just special kind of addition. So once you understand that, so 57 times 21 simply means what? Now, so there are two conventions. 4 times 7, you either say is adding 4 to itself 7 times, or adding 7 to itself 4 times. But you have to agree on the convention once and for all. To us, it's this tells how many times you add the second number. Okay? This convention, nothing more. Then, so in that case, 57 times 21 means only one thing, namely, add 21 plus 21, 57 times. Good. Now, we don't worry about exactly what it is. But, you know, in principle, there's no problem finding what it is, right? Keep counting. How high can you get? That's right. So now that's the other thing I'm trying to impress on you. We should establish this good habit from the beginning, which is that too often in school mathematics, that's a legacy of the textbook. We tell students to do things without telling them what they're doing. Do you agree or not? Yeah. For example, to make a long story short, you tell them, well, it's easy, right? That's what it is. Except that that's the easy part. The hard part is, what is this? What is this? What is this? Well, the fact that you have to think about it makes my point, right?
3/4.
That's exactly what I'm trying to tell you. This is something that's so basic, it should be just rattle off. You want to know what it is that portion. That's the other one. But it's not in the habit of our textbooks to tell you, well, before you do anything, let me tell you what it is first. What are you doing? Here is just saying, don't ask and don't tell. Just do it.
Oh, so it's 3/4 by 21/5 time.
There's no such thing, right? 3/4. You add to itself 3/4 times, right? There's no such thing. Right? So this is the bad habit promoted by textbooks for ages. Don't worry about what it is. Do it.
1/5.
And you think that's harmless, but it's not harmless. Look at the amount of non-learning taking place. So we want to get you out of that. You want to get your students out of that. So everything we do, you observe. Now, I would say it once, maybe I'll say it again. Obviously, I may. Whatever we do, we first ask, what is it? Never mind what the answer is. I don't care about that. But if you don't know what it is, don't do anything. You want me to do something? Tell me what it is. So that's why 4 times 7 to us is completely unambiguous. It's 7 plus 7 plus 7 plus 7. So of course, should I have been sermonizing like this? That feel quite a bit. So let's turn to the exercises in chapter 1, I think it's page 30, 39, is it? 39,
35.
35, yeah. 35, yeah. Look at exercise number 9. This is now 3rd grade, as you know. It's the first introduction to multiplication. Right? This is how a typical school textbook talks about multiplication of whole numbers. I want you to read through it. It says 36. Number 9.
Number 9 only.
Number 9 only. Number 9. Exercise number 9. Read it. I want you to read it.
Wow.
Wait a minute. Don't say, oh my God. You've seen it many times before. It's what every book does. I'm not making it up. I've seen many books.
Wow.
Now, have you read through it? Yeah. So let's analyze it step by step. So it's supposed to explain multiplication to 3rd grader, right? So let me ask you, reading through this, never mind the young kids, innocent young kids, you as a teacher read through this, what is multiplication to do? An operation using at least 2 numbers to find another number called a product. What about addition? Is that different according to this?
No.
2 numbers, right? Is it?
Yeah.
And secondly, product. The answer in the bottom. Well, you don't know what multiplication is. Why do you know what a product is?
Well, you know it's the answer.
Well, an operation is something you go to the doctor for anyway.
That's right. You pay a lot of money. Yeah. So this is exactly this culture in school economics. This is what you were taught. And don't say no. I know this. All the textbooks are like this. At least all the major ones I've seen. I don't know. And this is how we're brought up, right? Now look at the next thing in the text itself. This, how many are in 4 groups of 6? Now that's sensible. That's a sensible question, right? Well, of course, if you have a sensible answer, the 4 groups of 6, how many are there? There's 6 plus 6 plus 6 plus 6, no? Right? Well, that would be okay. But look what is this? You can use multiplication to solve the problem. Well, it says you can, that means what? You don't have to.
You don't have to, yeah.
So you don't have to, then what do you do? What do you do? Does it say? How do you read a book like this? I mean, it says something halfway, and then let you guess what the other half is. How can students learn?
4.
Right? And then it says use cubes to model the problem and record the answer to the problem. Now look, it doesn't even say how you want to solve the problem. It just says Here is how you record the problem, answer to the problem. 6 times 4.
Why do we switch numbers?
Yeah.
Well, they can have some different. Maybe their convention is 6 times 4 is 6 plus 6 plus 6. As I said, the two conventions, right? So I'll let that go on that. But there's no reason you should explain multiplication on this basis. Right? Now go on. I mean, look at the next one. If Helena practices singing 3 hours each day for a week, how many hours will she practice altogether? It says find 3 times 7. Why? What do you mean find 3 times 7? Why should I find that? Well, the next thing, by the way, is really bad. There's more than one way. No, actually, there's nothing wrong with it. You want people to know how to solve a problem many ways, right? But look at how it's done. First way, method 1, right? It's that one. Method 2 is the other one. Well, you said, right? It says 2 ways. That means these 2 things are different, right? If they're different, you say there are 2 ways and 2 different ways, and they give the same answer, then you should explain why they give the same answer. That's the first reaction. Second reaction. Do you think these are 2 different methods?
No.
What they are saying is that here is a definition of multiplication. Right? That's what we're trying to say. That's not a different method. I'm telling you this is new notation. That's all you want to say. Don't say it's 2 different methods. Everywhere you turn, you can see why there's non-learning in mathematics classes. With textbooks like that, even if you had known something, it would be immediately reduced to more. Remember, like this is just hopeless. That I want you to get you out of. Don't do it with your students.